Conditional probability is still finding the probability of a single event, but it's conditional upon a previous event. So the probability that event B occurs given that event A has occurred, that's called conditional probability. So the probability of this event B given A is written as probability of B given A with a line through it there. So A and B are independent events if the probability of that second event equals the conditional probability, because that second event doesn't depend on the occurrence of the first. So it sounds a lot more complicated than it is. So if we look at the first example, sometimes they have a chart for you. Sometimes you have to understand the situation a little better to understand what's going on. But in example 1, it took a survey of 28 students whether or not they do household chores at night. So number 1 is just a simple probability. Find the probability of a student doing a chore. So probability that student does a chore. And you guys don't have to write this part out. I just like to write it out. So out of the 28 students, how many said, yes, we do a chore? 7 plus 7, which is 14 out of 28. So that would reduce to 1/2, or 50%. Okay. So number 2, that was not a conditional probability example, but number 2, it says find the probability of a student doing a chore given that the student was a male. So it has it written out here. Probability that a student does a chore given that they are male. So the given is the total that we are using. So given the male number of students, so 7 plus 8 is 15, how many of them said, yes, we do a chore? 7 of them. So that is it. So 7 out of 15, if you guys divide that, would be 47%. So number 3, find the probability of a student not doing a chore given that they were female. So given that they're a female, what's the probability that they didn't do a chore? So out of the female total, 13, how many of them don't do a chore? 6 of them. So 6 out of 13, if you guys divide that, would be 46%. So when they give you guys a chart, it's really not too complicated. Now we do have a formula down here for conditional probability of B given A. So what we have to do is find the probability of A and B. So we find that overlap and divide it by the probability of the first event. That's the equation. I think that makes it more complicated than we need to. I like to take it back to Venn diagrams. So if we look at problem 3, which was the one we just did, find the probability of a student not doing a chore, given that the student was a female, it goes through and walks you through that formula. So the probability of A, that they are female, there were 13 females. Not doing a chore, there were 14 people that didn't do a chore. So, probability of A and B was that 6 out of 28. So that's what goes on the top of your fraction if you guys choose to do it this way. And then you would divide it by the probability of A, which was 13 out of 28. So, dividing by a fraction is really multiplying by the reciprocal. So you would get 6/28 times 28 over 13, which just simplifies to 6 out of 13, which we got to be our answer. Does that seem complicated? Yes. So what I like to do is just kind of look at it at a Venn diagram. So if I created two Venn diagrams for our females and for people not doing chores, those are our two events. The first Venn diagram here is for students not doing chores. So that was the 14 students that don't do a chore at night. My other circle are the females. There are 14 females. Or not 14, 13 females. Now the middle is the overlap, and I know that because of my chart. There were 6 females that did not do a chore, so they're female and they don't do chores. So that is the overlap. So because the given or the total is the 13, I use that circle. So, given that they are females, how many of them don't do a chore? 6. 6 out of 13. So whether you guys want to use the formula or Venn diagrams, I think they both kind of work the same way. The Venn diagrams are a lot more helpful if they are dependent events of one another, but they work for both. So I know the next page is practice, but I want to do 2 of them with you guys. So let's do number 1 and number 2. So it says you roll 2 dice. The first die shows a 1 and the other die rolls under the table and you cannot see it. So what is the probability that both die show a 1? So your formula would be the event of the first die being a 1, so 1/6, and the event of the second die being a 1, so 1 out of 6, and you divide it by that first event being a 1 out of 6, literally the number 1. So what would happen here is they would actually cancel, and the probability would just be 1/6. If you guys use a Venn diagram, so I made 2 circles for each die. So the first die, both of them have 6 numbers on them, so both of them have 6 outcomes. But if you want both of them to have a 1, the overlap here, if you move them, that overlap in the middle is going to be one outcome where they would both have a 1 out of 6. The first one has one option, the second die has one option for there to be a 1. So, again, your total would then be 1 out of 6. So that would be 17% if you guys divided it. Now, those events were independent of one another, so when they're independent, that's what we're saying. It's just the probability of the second event because they don't affect one another. Now, number 2, they are dependent events. So let's look at that one. So, for number 2, you decide to tell your fortune by drawing 2 cards from a standard deck of 52 cards. So what is the probability of drawing 2 cards of the same suit in a row? The cards are not replaced in the deck. So the probability of your first event, and we are drawing cards of the same suit. So 13 cards in a suit. So probability of your first event is 13 out of 52. Now if the card is not replaced, the probability of picking that second card, there's 1 less in the suit and 1 less card in the deck. So 12 out of 51. And we're going to divide that by our first event, given the first event was from that same suit. So what happens is that because 13 13 divided by 52 over 13 divided by 52 is the same, we can actually cancel them out. So when your events are dependent of one another, it's the probability of that second event given that that first one happened, because those two items cancel each other out. So the probability here would be 12 out of 51. We could reduce that to 4/17. Again, not overly concerned about it though. Reducing your fraction. So 12 divided by 51 would give you guys 23 or 24% if you guys rounded up. So conditional probability, we're still finding the probability of a single event. It's just we're finding the probability of that event given something already happening. So if it's independent, it just is the probability of the first event because they don't affect one another. But if they're dependent, it's just the probability of the second given that that first event occurred. So go ahead and try the last four based off of those two examples.